up until 12. Okay, let me just get this set up. And to share screen. Okay, does everyone see it in presenter mode?
It looks good.
Oh, it did look good? Okay.
Yeah.
Okay.
Perfect.
So, everyone that's on Zoom and the 3 people here in person, shout out to the Center for Global Health. So today I was asked to give a presentation on the basics of GIS and kind of how can it be used within global and public health. So some of these topics would take a week or 2 to typically talk about. So it's more, I just kind of show a little shiny thing, jump to the next shiny thing. So talk about a lot of different topics. So just jump in throughout the presentation if you have questions. Thank you, Alexa, for setting this up. And yeah, my background is in machine learning and GIS. Once I took my first mapping course, I kind of realized this is what I wanted to do. And my PhD was more within soil science, but it's kind of same methods can be used everywhere. So, get to the next slide. There we go. This is probably a map that everyone has seen and probably a lot more familiar with it than I am. Every GIS course, we start off with this map and we talk about it from a spatial context. When I took my first intro to EPI course last year, it was interesting to see it from a health perspective. So in GIS, we talk about if location matters, then you should do some kind of spatial analysis. If John Snow didn't put this on a map, we wouldn't have been able to tell which of the pumps was the one that was getting everyone sick in London at the time. So if we overlay it with a spatial analysis of doing a hotspot of where the number of people are and where they're getting sick, we can see that it is happening right next to the Broad Street pump. Again, I won't go into it in further detail because the public health people probably know it much better than I do. But so what is GIS? GIS stands for Geographic Information Systems, and kind of nowadays it's going more into geographic information sciences because it's becoming its own whole field by itself. And we typically think about with GIS is we think about a map. As soon as I tell people that I make maps, first thing they think cartography. And that is a big aspect, but without a build or a software or online application or wherever we can make the map doesn't really mean much. So there's a whole bunch of softwares out there. We'll talk about that more in a second. But the software is where we can actually visualize the data. And you might have all the villages that in your analysis, every house with GPS location. But if you don't actually do a geospatial analysis, then it doesn't really matter. So that's a big portion of GIS is the analysis. So this can be determining the differences between the west side and east side of the villages. Are you more similar or less similar to your neighbors? There's a lot that you can do with your data. And that's kind of what you want to do because pretty maps are great, but we want to know, is there any kind of significance to what we're seeing? And then the last portion, which you don't really need to worry about, is the data administration. Data is a little bit more complicated in the spatial realm. It's not just a CSV file, but there's always someone on campus who handles that for us. So it's kind of a nice portion to not think about. Now, the leading company, if talk to most GIS people, the leading company would be Esri. They make a software called ArcPro, and that's kind of what everyone is using for the most part. It can do a little bit of everything, gives you nice, pretty maps. It can do your analysis. But I typed in, when I was making this presentation, most common GIS softwares, and there were 50 that popped up, and there's probably much more. And each of those typically give one specific thing that they do within GIS. Esri is kind of a little bit of everything. The issue with Esri is that they are very expensive, so their licensing is kind of an issue, but through the university, you do get the license, so you don't really have to worry about that. Now, if you're one to stick with open software, then you would go more on QGIS side. It's not as fancy as Esri, but it can do pretty much everything. So if you think of Microsoft Word 1998, that would be QGIS. If you think about Microsoft Office kind of 2020, that would be more Esri. So they can do pretty much the same thing, but Esri has a little bit nicer user interface. And so these are ways that you can click, make your maps, do all of these things with a mouse, but you can also connect other programming languages like Python and R and do things in a more automated fashion, especially if you have to repeat yourself quite a bit. So, and here's just a few others that I threw up. I won't go really into them, but they each have their own specific aspect that they do within GIS. So Saga, for example, is a great way of getting derivatives of certain maps, and you can create a whole bunch of extra maps just through Saga, but you wouldn't create a map through it. So each software kind of has their own specialty. So jumping, we'll be doing that a lot. We're just going to be kind of jumping from topic to topic. We're going to talk about common terms, just a few that you might need to know or that you hear. And these first three, the coordinate system, datum, and projection, is something that you would typically spend a week or two within a class. So a coordinate system is just a way of how do we tell where we are in space in relation to other aspects in space. So with that, you have a 3D model. So we have the globe, and we need to turn it into a 2D surface if we are trying to make a map or do some kind of analysis, let's say for a publication. So we have these datum points, which is how we can help build our models to go from 3D surface to 2D surface. And if you ever go hiking to top of peaks, or if you drive to Pikes Peak or Mount Evans or any other kind of peak place, you'll usually see this metal disc within a rock. And using those is how we can tell or how we can model the Earth's surface. So if we go to a library or some kind of fancy room and we see a globe that we've all seen growing up, it is a way oversimplification of the Earth. So we can see here what the Earth's surface actually is, and this ellipsoid or globe is very simple compared to it. So using datum points and a lot of math, we get these things called geoids, and that is a more accurate representation of the Earth's surface. Now we have to also think about how we're going to what's called project it onto a 2D surface. So when you go from a 3D surface to a 2D surface, you're going to have some kind of distortion that you have to think about. And we'll talk about that more in a few slides. With this group of people, another common term that might be relevant is geocoding. So this is a way of going from street addresses to points. And that is quite helpful if you get an address for every person in a village. You can quickly go from that to a point on a map. But it only really works if there's a well-defined street address. I've lived in some pretty remote locations where I'm the third hut from the front, and then it gets a little bit more complicated to use geocoding. And then we'll talk about this further in the presentation, but the two main different kinds of data is we have raster data and vector data. Raster data is a grid. If we think of, if you take a picture and that picture is a bunch of pixels, that is essentially raster data. So we have this grid that is full of cells. Each cell only has one value, and that is our raster data. Vector data is our points, lines, and polygons. So typically when you go to a house, you do a survey, you'd get their latitude, longitude. That would be an example of vector data. And then the most common way that you share vector data is with a shapefile. So these are just terms that you might hear if you're talking to a GIS person about getting your analysis up and running. They might throw these words around. So projections, again, something that we would talk about for probably at least 2 weeks in a class, but we have this 3D surface and we got to turn it into a 2D surface. So this right here is, you can see a few, moving that out of the way. You can see here are just a few examples of how we go from a 3D model to a flat map. And there's going to be 4 kinds of distortions that you have to try to minimize when you're doing your work. So you have the shape, area, distance, and direction. So each of these blue circles on the maps on a 3D surface are exactly the same, but we can see that they change depending on what kind of projection that we do. So growing up in the US, in our elementary, middle schools, we typically see this kind of map. This is a Mercator map. And it each map kind of has their pros and cons. But this one overrepresents land mass in North America. And it's been an issue because people think, for example, Greenland is the same size as Africa. But that's not true, because as we get further, or as we get closer to the poles, the land elongates more. And that's because we're using this cylindrical projection right here. So this is something that you would think about when you do your analysis, because if you are interested in area, you would want to do a projection that is minimizing the distortion within area, but maybe it's more distorted within direction. But that might not be important in your analysis. So here's an example of the US in 4 different projections. And we can see that depending on the projection that you use, the shape, size, orientation, direction, everything kind of just changes a little bit. So the like a projection that we would use within, for example, within Tennessee, which is a more west-east state, you would want to use a different projection than Florida, which is more north-south. Or a US projection you wouldn't want to use for, let's say, Germany. You're going to want to use something that is as specific as possible for your location. Here's briefly, we're just going to be talking about making maps and picking colors next. So here, not everything is necessarily important to use, but there are a few aspects that are for sure something you want to think about. So here, the data frame. So this is actually the spatial data that we are looking at. Typically, you want to have a legend, because without a legend, we wouldn't know what the different colors represent. Map title, maybe you want to use, maybe not. If you have a caption within your figure, if this is in a publication, you might not need a title. North arrow is quite important. There's many times where people forget that, and it's actually east is the one that's up. So you think you're going north, but in reality, you're going east. Scale bar, most of these things are quite intuitive, but it's important to know, how much of this color is it from here, from middle of Montana to North Dakota. You could use a scale bar to determine. If you put in your citation for your data, borderline, that's just kind of preference. But a very important one, especially if you're working in a very small location in a part of the world that maybe people aren't as familiar with, you would want an inset map so people can kind of orient themselves. Where are they in the world? So we can see here, this is the portion of the map that we are displaying. And then people can see, oh, okay, so that's, middle of North America. So picking colors, when I took my first cartography course, my professor, she was a color fiend, and we talked about colors for 2 weeks. And this is important because when we look at certain colors, we intuitively think of something. So if you see blue on a map, you would typically think rivers. But I've seen maps where they use roads or they use blue for roads, and then it gets kind of confusing. If you are a map nerd like myself, there's a lot of funny map fails through news sites, and there are some really bad ones out there where the news is trying to present something, but they're kind of misrepresenting what they're doing. So when we think of color, if we saw this map, right now, don't worry about really what it means, but we look at red and we think that's probably a worse location than yellow. So this is an important thing to think about when you're doing your colors, because if I had this map on the right where red is low, and I could put a legend up and everything, so I technically wouldn't be lying, but people intuitively see red and think, you know, higher risk, danger. So it's just something to think about. There's a whole series of books called Lying with Maps, and it's very interesting of how you can deceive people with just color alone. And another thing to think about when picking colors is red-green color blindness is much more prominent than people think in society. So even though it's a good way of showing red bad, green good, you would want to do something else. One of my first maps I ever made for a supervisor, gave it to him, he's red-green colorblind. All that work I did was a waste and I had to go redo it. So switching topics again, we are going to talk about vector and raster data. So if we have this image here of a building, we can represent it with a polygon, or we can represent it with cells. And we can see that with the cells, the outline of the building isn't as accurate, but it is, there's maybe benefits that you can do if you have raster data. So vector data, we have our points, which if you think of a house location, you would collect maybe latitude, longitude, and that would be a point. This could also be where you found a mosquito, or where there's hospitals, or any single location that you want to represent would be a point. Lines are multiple points that are connected. And this is typically roads or streams. This can also be migration patterns. This can be anything where there's kind of, it's not connected, because if they're connected, then we would have that as a polygon. So that's 3 or more points that are connected. This can be the outline of a country, states, buildings, an area of interest that you are looking at. That would, for example, be a polygon. So here is an example of a map that is showing rural health clinics across the United States. And then that's the points, and the color is rural and non-rural. So rural is green, yellow is non-rural. So we can see here that they're showing using points where rural sites are, and then using polygons, we have our state outline. It's very difficult to see, but here there's the county outlines, and those are colored dependent on if they're rural or non-rural. So this map shows a lot of good things. There's a few things that, you know, you have to make compromises every time you make a map. So for example, when I was talking about scale, right now, it looks like Puerto Rico is the same size as Alaska, which, you know, is not correct. But that's, you know, this is a zoomed in map, but we don't know what is the scale in relation. That might be important, that might not be important, just things to think about. And then the same with these islands, all these territories, it is very difficult to tell, you know, are these rural or non-rural locations? So maybe with this map, these shouldn't have been shown because they're not actually lending any information. So that was points and polygons. Here we have points as location and lines as in roads. So I'd say lines are kind of underutilized a lot within analysis, but if you had the location of certain services, so let's say hospitals, and you had the location of people's houses, you could determine using a road, how long would it take to get from point A to point B? You don't have to do just a straight line distance. And so then you could come up with a metric of, person A has easier access to this service than person B. A couple ways of representing your data. Here we have what's called dot density. So each of these dots are representing 50,000 people. So you can look and you can quickly tell where there's more people in the US than other locations. You can also use proportional data. So here, every county is now getting 1 point, but that point changes in size. So it's this is proportional data, and it's a little bit more complicated because it looks like in this area, there actually might be a lot of people, but they could all just be very small points. Whereas here, we can see kind of where they're aggregating. You can represent your data. Let's say you had yes, no information. So yes could be blue, no could be red. And then the value of how many people said yes or how many people said no could be the size of your point. And another way, you could just color in the entire county. So here, darker colors are representing a higher percentage of population between the ages of 5 to 17. So just a couple of ways that you can show your data depending on kind of what you want to represent on the map. Switching to rasters. So this is my preference of data because you can do statistics a little bit easier because you have this uniform grid where each pixel only has one value. So here, if we had these 3 grids that are on top of each other, each one only has one value, we could do something easily and say, what is the minimum value at each location that's pretty much under here? So we would, if we drew a line all the way through, this would be 3.8. If we drew a line all the way through here, it'd be 0.9. And you could do that everywhere. And we'll talk more about that kind of calculation a little bit later. So another thing to think about is your resolution of your data. So the more cells you have, the more realistic it is, or representing the item more realistically. So we can see here, this looks like this shape, whereas here we're kind of getting pretty abstract now. So to represent this with a picture, so this is a picture of a park. We can see there's a building, a road, or like a little path and a dock. And as we change the pixels, you can still see what we're looking at, but it gets a little bit more fuzzy. And then the further you get away from it, it's very difficult to tell what you're looking at. But if we're trying to do an analysis for the entire world, we wouldn't want to have this much information because that's just going to kind of blow up your computer. And here, if we are only interested in what's light and what's dark, we can still tell what is light versus what is dark. So if we look at a picture, a colored picture, this is actually a combination of 3 rasters where it is some value of red, green, and blue. And by combining that together is how we get our colored map. There's so many different kinds of raster data that's out there in gridded form. So a very common one we would think about is elevation. So every single cell just has how many meters above sea level at that location. Anytime that there's going to be climate data, typically that's going to be some kind of raster. You can get things from satellites. So if we have vegetation or not vegetation, or it can be more specific as, is it forested, brushland, prairie, all of this stuff can be represented quite easily within raster. And then also, for example, if we wanted to know what's rural or non-rural, that would just maybe be yes or no at each cell. And then just because you have one layer doesn't mean you can't do more with it. So this one right here is an elevation map, and you can get slope from that quite easily. If you are interested in where water would flow like through a village, or if there's any spots where water might pool, you can get that information from a raster. If you're interested in what's north or south facing, for example, if you are looking at a certain vector and you know their preference is, let's say, north facing, then you could use this aspect map to look at where's north facing versus south facing. So now we're going to just go through a few different functions that are kind of common within GIS, and we'll see especially this buffer one in an example later on through a WHO map. But a buffer is just putting pretty much a circle of a certain size around your data. So if these red dots right here were locations of houses, and you had another set of points which were grocery stores, you could put a buffer around each house that, let's say, 500 meters, and say how many of these houses do not have a grocery store within 500 meters. Very simple analysis that can be done, and then you could feed that into your, if that's within your model, yes, no, these houses have grocery store access or don't. So buffer is quite common. Then let's say, for example, this clip feature is your buffer. You could get rid of all of the information you're not interested in, and we can then get rid of everything that is not pertinent in our analysis, and we can just focus on our specific area. And this is helpful because if you're working within a, let's say, a small village that's a few kilometers, you wouldn't, and you got a data set that was global, you wouldn't want to be working with the global data set. You would want to clip it so you're only looking at what's in your village. Then you can get all of your normal, lovely statistical analysis from your data. You can look at the distribution, you can get mean value, max, min, you can get pretty much everything that you want, just on a regular statistical side from your spatial data as well. And then with raster data, what you can do is you can form zones. So this could be, let's say, one community, this could be another community, this could be another community. If you're trying to simplify your data a little bit, and then you could take a mean value. So you could say in community 3, the mean value for X is 4. And then that could be used later on in another, in your model or whatever analysis. Here, let's say we have a point location of where we found mosquitoes, and we wanted to do, and we wanted to know, would there be mosquitoes here, yes or no? We have to somehow go from points to a continuous surface. So some more simplified ways are using interpolation and kriging. And one thing you kind of always learn about in GIS is Tobler's first law, which is everything is related to everything else, but near things are more related than distant things. So if you take one step to the right, you would assume the elevation is going to be more similar than if you took 10,000 steps to the right. So those are going to be less related than things that are more near. So there's a lot of different ways that this can be done, and they all give you different predictions. So here we can see that the surface is not the same depending on what method that we're using. Some are simpler, some are a little bit more math heavy. So recently I had to create a risk map. So what we saw earlier with that red being high, I had to create a risk map of where arbovirus could be an issue in blood transfusion. So I was given this table right here, and I was giving all of the maps that I needed. So what we had was, for example, precipitation, which goes from 0 to over 1700. And they need to be reclassified into what they're calling this risk scale. So if there is a range of 0 to 50, we would say the risk is going to be 0. So I take all of my data, turn them into rasters, reclassify them, and then when I add all of these maps up, we get something like this. So what we see is that areas in red have a higher risk of arbovirus transmission within blood fusion than areas in blue. And this, once I got my data all ready and kind of easy to work with, it took 10 minutes. And now this is going to be used within further analysis within that paper. So when we think about modeling, you can do your modeling spatially as well, but things are not expected to be the same across space. So when we do ordinary least squared, we have one global model, but what we want to do with spatial analysis is we want to use our neighbors as a prediction rather than everywhere, because as I just said, things farther away are more likely going to be less like each other than things that are right next to each other. So this GWR, kind of an older method, but called geographic weighted regression. And you use your neighbors to create your model. So here we can see areas where the model is doing well versus areas where the model is not doing well. Areas in red, high R squared value, areas in blue, low R squared value. So now here's just going to be a few examples of kind of a little bit more complicated methods using machine learning. This is just stuff from my PhD where we wanted to figure out where in Denmark are areas more related to each other using these variables right here and a clustering method of fuzzy C means. I could determine that these are the 3 different regions within Denmark. So I can now use these regions in further analysis later on. You can also do, so previously was unsupervised learning, now this is supervised learning. So using random forest, I was able to make predictions across all of Denmark because we wanted to know, so these points are yield values for winter wheat across Denmark. So what would be the yield in this specific location? So by combining soil, topography, and climate, I was able to get a prediction everywhere. So this is something you could think about if you want to know in your specific area, are certain vectors present or not, because you would have presence absence data, and you could make this prediction everywhere because we wouldn't know, for example, would there most likely be a mosquito here or not. Then this is being recorded, so you can just pre-watch or watch the recording again, or send me an email if you're interested in this list. But I just came up with a list of resources that could be helpful within your analysis. So a lot of things now, if you are interested, they're already globally available. Of course, every country might have their own specific data set, which is going to be better. So for the US, there's amazing data for demographic information, stuff, I believe, all the way down to the census tract. So it's very, very specific. But you can get your administrative areas, so states, counties, census tracts, all that stuff. You can get all of this information through this global administrative areas website. For environmental data, we have elevation. So that's DEM for digital elevation model. This is easily accessible through the USGS. A lot of this data comes through the USGS. Anytime that you want to get climate data, there's so many different resources out there now. This could be past data, this could be future projections. It could be what is the wettest month in the coldest period or something like that. There's a lot of different things that you could get just from climate data, and there are so many different resources for that. There's also a lot of soil information. So if you are interested in where water might potentially pool after a heavy rainfall, it's important to think about the soil because certain soil properties are going to either let water drain or not drain easier. Satellite information, again, through USGS, there's so many different satellites out there and can be used for a lot of different aspects. So if you have, you want to know areas that are vegetated versus non-vegetated, you can do that through satellite imagery quite easily now. Species distribution, again, it's every country might have their own information a little bit more like higher resolution, but through USGS, you can get presence absence data for quite a few different species. Demographic data is, of course, very important for this group of people. What is the average age in a certain area? What is the spread of age? Through World Pop, you can get poverty information, you can get population density. There's a lot of different variables out there that you can already use and just start incorporating that into your analysis. And then, as I said, each country has their own information. Each state also has their own information. So Colorado has some pretty good ones on health data. There's also water quality data. There's a lot of pretty cool resources out there. And then a more recent one is through Facebook. It's called Data for Good. And they have been coming up with quite a few metrics using Facebook information. So if you have your location services on through Twitter, Instagram, Facebook, they're actually using that information now to come up with these metrics. So through this data, they have shown with a crisis, where do people go? From what country would they go to a different country? So you can see, you know, country A is, connects more, like they talk to country B more than they do to country C. And all this stuff is with Facebook. They've done quite a few network analyses with Twitter, where if you have your location service on and you tweet something, they can see who was around you at that time. So for example, if you were sick, you go out in public, you tweet something, they can look to see who was around you and potentially could be sick from that as well. From the people that I've been working with at the Center for Global Health, a lot of this stuff is survey data. So the minimum thing that I have been kind of pushing is putting the latitude and longitude in 2 different columns, because then it's easier for the analysis and spot checking. I know a lot of people use RedCap, but if there isn't as sensitive information, through Esri, there's quite a few apps you can use that are kind of like SurveyMonkey, but it goes straight to a map once you click send. So it's quite nice to have dashboards that just automatically update once you're done with the survey. And then, you know, people can, that aren't in the field, they can see like, okay, we got 3 more surveys today. We can start doing this new analysis or whatever. There's the GIS apps are quite connected seamlessly. And then here, another app is, so they're called story maps, and this is through Esri. This is an example from WHO, and they're quite nice because you can have the prettiest, best looking map ever, but if no one is going to take that and go further with it, then it doesn't really do much. And a lot of people can't read maps because they might not have grown up looking at maps. So what we can do is we can make these articles that go with it. And so this article, again called story map, is you can put whatever information with your map. So as you scroll, things change. So here is a story map within a story map. And this is a dashboard that updates as information comes in. And so as you continue to scroll, there's different layers that you can work with. They kind of set it up slightly weird. So for some reason, it's not exactly working the best, but as you can see, like you could have different layers And all of this stuff is explaining. This stuff can be given to, as deliverables or to stakeholders to show like why we did the work that we did. There's a lot more information than just one map. So as you scroll, you can see like things are interactive. So if we click here, we can see that that's the name of the river. So this circle right here is a buffer around that hospital. So distance to hospital with ICU, 50 kilometers. So you could see, you know, how many houses are within 50 kilometers of a hospital. And then there's all this information. So this is like the name of the hospital, and people can look through and get all of the information outside of just the text on the side. You can put in pictures, you can put in videos, infographics, but this was the main one I wanted to show. So if these were positive cases and they put a buffer around each of the positive cases that they found, they could look to see which areas we need to survey more than other areas. So this is potentially, you know, higher risk of other people getting sick than further away. And so with satellite imagery, you can get building footprints across the world now quite easily. And we can then go, so we know this person at this house or infrastructure, wherever they found them, was sick. So you could go to each of these houses and, you know, survey them as well to see if they got sick or not. Yeah, here's a video, here's infographics, and you can just do a lot of information with this one story map. I wanted to see if this was going to load. Yeah. So again, as you scroll, we can see, so this is population data. So areas that are more densely populated versus other areas. And they're trying to figure out where is the best place to put mobile clinics so that they can distribute vaccines. And so they have their road network, they have distance to hospitals, they can figure out where should we put our different mobile units, how many people is that going to affect. You know, if let's say this is a more densely populated area, you maybe, and you only have one mobile clinic, you might not want to put it out in the middle of nowhere where people have to come to you. But yeah, so this is what's called story map. And once you have your maps ready and kind of like set up in a certain way, then it's quite easy. The hard part is just getting your maps ready. Yeah, so again, as I said, through the university, we have licensing for Esri products. So you can contact through whatever university and get that. But there's a lot of resources online of how to start actually bringing in data within a GIS software. So here's just a few different ones, one for Esri and one for QGIS. But if you need any help in the future, just reach out to me. Here's my email. We can talk about analysis, you know, if you need maps made, or if you just want to bring in any kind of spatial aspect into your project, I'm always happy to talk maps. So that is end of presentation. I know it's kind of a little bit of everything. So I hope you're all still there with me, but yes, I will take any questions. Yes. Yeah. So, question was, okay, I need to stop sharing my screen. There we go. 2 seconds. So the question so far was to show the precipitation data, you said, for Africa. Yes. Mm-hmm.
So if I want to make a change for the specific location of each class, I just have to click on it and then go to what and manually change it, and I can click on the geolocation, the geolocation, and it will automatically update the latitude. We might be able to do something like that. That's easy for if I want to see the changes. So just open it and then refresh it.
Yeah. So question was pretty much how do you show precipitation data throughout the year, since that's a dynamic variable? Yeah. So I was sent the maps, so I assume they got some mean value, or they might have gotten, you know, a minimum value or whatever. But you could get it for every month. You could get it, so you could just create, let's say, 12 different maps for like one for each month, and then see how things change from there. I mean, it would be a little difficult. I mean, there's future projections, so you could use that kind of information. But with it being live, for this kind of scale would be a little bit harder. But if you were working within a smaller location and you had a weather station, you could then use your weather station to do this kind of stuff. Yeah.
Is there any other way to make it? It's always the citation.
Not exactly sure I understand the question. So what's a better way of representing the data? So you can put it into classes. So if you know you are interested in, I don't think I have a good example. Yes. Okay, I see what you're saying. I missed it somewhere. It is here. It is. Yeah. So you're saying what is it?
I know that exists, but is there another option? Because it's always that one.
Yeah. So question was, is there another way of showing this kind of information? So here we have classes that it's in. It could be continuous if that's how your data is represented. So it would just be a gradient scale. But this right here would be the most common way, just because you can then quickly tell like where's the darker areas versus the lighter areas. But the way you break it up can change drastically. So it can be, you could use standard deviations, you could use a minimum maximum, you can do what's called natural Jenkins, I think is what it's called, and that finds kind of what it thinks is the optimal breakpoints. Mm-hmm. Yeah, so you can, if let's say you had data that went from 0 to 10, class 1 could be 0 to 5, or class 1 could be 0 to 1. So all of these little changes, this is the whole like lying with maps, because you can really over-represent something or under-represent depending on what your scale is within your legend. Yes. Okay, so a question from Christopher. It says, I like how you, oh, okay, that wasn't a question. But yeah, so machine learning is a great way of incorporating, or it's a great way of using spatial data, because a lot of times we have only one spot because we're talking to a person, or we are in a field and we collect one point of data. But what is it 2 miles from us? We need to make that prediction, and using machine learning is quite helpful to make those predictions. And it's very straightforward because the actual analysis is just using regular machine learning, but you just kind of do it in a semi-spatial way. So, but there's a lot of different statistics. Like that wasn't even something I went into. There's a crazy amount of spatial statistics in like within GIS softwares. For a 10-year period. Okay, so question is there a best practice way to present data over a 10-year period with different values? So depends at the resolution of your data. So is this every month? Is this every year? But what you can do is you can create, let's say 10 different maps and then turn it into an animation if you're interested of how does it change over time. You can also, with these through Esri products, you could just have all 10 of them on top of each other, and then you can click some of them on or off, depending if you wanted to compare like year 2 to year 7. But animations are kind of a great way if you're trying to show how things are changing.
Question. If the value, so if you have different scales, or basically to present the data, it would be best to present them on different scales. Would they all need to have the same scale?
Probably from a visualization aspect. Yeah, just, well, I guess. Well, I guess, what do you mean by scale? Do you mean like resolution of your data, if it's say precipitation?
Oh, I'm trying to present it over a 10-year period, and each year is variable in terms of how many cases there were per year. So I'm trying to decide if it's best to log transform the data to get it kind of on a similar scale yearly, or just present it on different scales, on, you know, like different case data kind of categories.
Yeah. I would say that's very data specific, unfortunately, because yeah, if year 1, let's say cases went from 0 to 100 and year 2 went from 0 to 1,000, you would, if you change the scale, then they might not be comparable. But for other properties, you might want to make them on the same scale, if that makes sense. Did that make sense? Jessica? Okay. Hopefully that made sense, if she is still there.
Can you hear me? Yes, that made sense. Thank
Okay,
you.
sorry.
Sorry, I had my AirPods in, so it might have disconnected. But yes, thanks so much for that.
Yes. Any other questions? We have just a minute or two. We got 1 minute. If there's any more questions. Well, if that is all, then you have my email. Shoot me an email if you want to ever talk spatial analysis or where certain data sets are. I can always help find that stuff. Usually if you just type in, let's say like population density shapefile with name of a country, it will pop up quite easily. So yes, thank you, Alexa, for setting this up. And if that is all, I guess we can in that there.